Right, so what we want to look at now is we want to look at line integrals. And so before I get into line integrals, let's just see an application, a physical application, well, from physics, where you actually will use a line integral. Okay, so and it comes from your definition of work in physics. Right, so if I have an object like this one over here, right, and a force is acting on it while the object is moving in a straight line, right, along a distance d, right, then the work done by the force is force times distance, right? So you want to notice here that this is a constant force, right? Okay, so your force isn't changing as you move along this straight line, right? And the next thing you want to notice is that the force is actually in exactly the same direction as, well, the direction of motion, right? Okay, so this is what I say over here, right? If I have a constant force, such as this one over here, right, and it moves an object a distance d, right, along a straight line, and where the force is acting in the direction of motion, right, then the work is force times distance, right? And if, well, here the force is, you could regard the force as just being a scalar, and the distance over here as a scalar, right? So your work is just going to be force times distance, which you can write as F times t, right? Okay, so this is a simple case, right? Which you know that work is equal to force times distance, right? Okay, so let's look at a slightly more complicated situation, right? You're gonna have the same object, right? Being it's gonna move through a displacement, through a distance d, right? Along a straight line, right? But the only difference over here is that this force is no longer acting in the direction of the motion, right? So the direction of motion in this case is this horizontal direction, and the force over here is not acting in that direction. But the idea is over here that as you move along, the same force that is, say, slanted like this keeps acting on the object, right, as it moves along the straight line, right? And how are you going to get your work done in this case? It's, well, it's fairly simple, right? What you're going to do is the force, you're just going to resolve. Okay, so now you're starting to think of this force as a vector, right? And you're going to resolve the force vector. You're going to get the component in the direction of the motion, right? And if you're just working with magnitudes, if the magnitude of this vector is just this f over here, when you resolve, you're going to get f cos theta, right? Remember, you're resolving to get a horizontal component over here. So it's f cos theta and then times d, right? So once you resolve the force in the horizontal direction, really you're just now using your result from up here, right? So you're going to get f cos theta times d, right? Okay, so what you want to notice is, well, we can use vectors to express this, right? Okay, so this f over here is the magnitude of the force vector f, right? So if you want, you could just look at this as your force vector f over here, right? Okay, so you're taking the magnitude of the force vector f, which is this f over here. You take in the magnitude of displacement, right? So this moving along a straight line like this, right? What you're doing is you're moving from this point to this point, and that point is a displacement, right? So that is what this boldface D is over here, right? But okay, what I have over here is magnitude of force and magnitude of displacement, which is just distance, right? So I need the magnitude of force. I need the magnitude of displacement, which is this over here. And then the angle cos theta that you got from resolving, right? Okay, so this is just an equivalent way of writing this, where you're just using a notation where you have a force vector F over here, and you now have a displacement vector over here, right? Okay, so, right, and once you have this, right, you want to notice that this is the same thing as the dot product of F and D, right? Okay, and you probably would have seen this in, say, a dynamics or mechanics course, right? If you're mechanical engineering. Right. Okay, so work is your force vector dotted with the displacement vector. And the nice thing about this is having this dot product, it actually also accounts for the fact that your force vector isn't necessarily in the same direction of the motion, right? So this expression over here will automatically resolve the vector for you, right? Okay. All right. Okay. So let's see something that's a little more probably a little more complicated than this last example that we did, right? Okay. So in this last example that we did, right, your your motion was in a straight line, and the force was constant, right? Even though it was acting at as an angle, right? As you were moving along a straight line, you still had the constant force acting at each point, right? Now, what can happen is this can get more complicated. What can happen is that the force vector can actually change, right? So this force vector, instead of being now constant, it could potentially change, right? And your displacement could possibly be no longer in a straight line, right? So that would be, say, this example over here, right? Right. Okay, so over here, what you're doing is you're moving, say, from this point over here, right? And you're moving along this parabola, which is no longer a straight line, right? You're moving along here, and you're going to move up to over here, right? And at each point on this parabola, you have a force vector acting, right? So this force vector is doing work for you, right? Let's put in some more force vector. So as you move along over here, you have different force vectors, right? Okay, so two things are happening, as I said, right? Your motion is no longer along a straight line, right? Your motion over here is now along a curve, right? And the next thing too is that your force vectors are actually changing, right? If you notice the force vector over here, it's different from the force vector over here, different from over here. So it's actually, the forces are actually decreasing, and then what happens over here is that it reverses direction, right? And starts to act in a different direction, right? And the force, the magnitudes of the forces are actually increasing again, right? Okay, but you still have force acting on the particle as it moves along this curve, right? So you still have work done by the forces, right? It's just that the forces are no longer constant. But it's the same sort of physical idea, right? You're still going to have work done as you move from this point over here to this point over here along the curve, right? Okay, so how are we going to deal with that, right? Well, you have to deal with two things over here, right? You have to deal first of all with the force changing, right? How do you model this change in force, right? Okay, so as you go from point to point, the force is changing, right? So as you go from one point on your trajectory to the next point in the trajectory, your force is changing, okay? Right, so how would you model that, right? Well, how you actually model that is you model the forces over here by using the entire plane and using a vector field, right? Okay, so you'd have a vector field throughout your plane, right? And well, what you only really care about is the vectors on the curve, right? But it's sort of hard to just specify what the vectors are along the curve only, right? So what you need to do is you need to use the entire vector field, right? And with the entire vector field, you just specify when you're doing a calculation. Now, all you really will care about is just the vectors on the curve C itself, right? So you wouldn't care about the entire vector field. You just care about the vectors on the curve itself, right? But the point is to model this variation, right, in the vectors as you move along the curve, right? What you need is you need to use a vector field, right? Okay, and the next thing you want to note that was different from your previous cases is that your motion isn't necessarily along a straight line, right? So these simple formulae over here for cases when the motion was in a straight line, right? If your motion is not in a straight line, right, like this over here, so this is definitely a curve, right? This is not a straight line. What you need to do is you need to also model that, right? Okay, and you have various ways, of course, to model a curve, right? But how we're going to do it in this class is we're going to describe this curve, this blue dashed line over here. Right? We're going to describe this blue dashed line by a parametric curve, right? Okay, so your curve C over here would be a parametric curve, right? Okay, so if I want to get work done from this point as I move along this curve C to get to this point, what I'm going to do is I'm going to use a line integral. And the line integral would, you need two things to work out your line integral. You'd need the forces, which is the vector field, right? And then you need a description of this curve C, right? And you need a parametric description, right? So you need to work out your line integral, you need a vector field, and then you need a parametric curve, right? And given those two things, you can work out your line integral, right? So you can get the work done as you go from this point over here to this point over here, right? Right. So your work done going from this point along your curve to this point over here by the forces that are acting on the particle as it moves along the trajectory. The work done is given by this formula over here, which is a line integral, right? So this expression over here is a line integral of your vector field, right? So it's the vector field, it's the entire vector, it's a line integral of the vector field, but all you're really looking at is the vectors along the curve C. So you'd be looking at these vectors over here. So it's a line integral of the vector field over your curve C over here, right? So the curve C is this blue dashed line over here, right? The curves, well, an example of the curve C is this blue dashed line here, right? Alright, okay, and it is, your work done is f dot dr, right? And you want to notice over here, this f dot dr, right? And you compare it to this expression over here, right? It's similar, well, it's very similar, right? You have force dotted with displacement, and you want to read this as you have force over here locally, right? And then what you're doing is you're taking a dot product with a small displacement as you move along your curve C, right? And then the integral is you add in those up, right? So that is what is said over here, right? The idea is that here what I have is I have motion from along this curve over here from this point to this point. So it's the same situation, basically, it's just a different example. And your forces are changing, right? And what they're explaining over here is that you approximate, right? So you consider, say, a displacement at a point. Well, well, this diagram is slightly inaccurate, right? But what you're doing is you're going to chop up this curve into various pieces, right? And you consider the displacement from one point to the next point, right? You work out what the dr is over there, and then the force, you can approximate the force over that displacement by you can approximate it over here by, say, this vector over here, and then you work out what f dot dr is for this one, right? And then you work out what f dot dr is for this one, f dot dr is for that one, and then you add them all up, right? And when you do it, when you take finer and finer approximations, what you will get is that the sum of these approximations will converge to the line integral, right? So that is what they're saying over here. That's really where this sort of formula comes from, right? But that's not really within the scope of this class. The scope of this class is you need to understand, well, what this is over here, the interpretation in terms of, say, work, right? Okay, so this is line integral of a vector field, right? And a vector field you could regard as representing forces, right? And C is a parametric curve, which is your trajectory, right? And when you do a line integral of your vector field along your trajectory over here, right, it'll get work done, provided you interpret in your vector field as forces, right, as a force field. All right, okay, so we saw interpretation of a line integral as work done along a parametric curve C, where work done by forces specified by a vector field as a particle moves along a parametric curve C, right? Okay, so that's your intuition, or that's an interpretation of what this line integral is, right? But now we want to actually calculate, right? So we want to be able to work out problems using line integrals. So the calculation, how you're going to evaluate your line integrals is just via this definition over here, right? Okay, so I have a vector field. The vector field for us needs to be continuous, but that is continuity of a vector field would just be all vector fields that we will look at in this class would be continuous vector fields, right? Right, so then in order to work out this line integral, well, you need a vector field and you need a curve C, right? And the curve C in this class is specified first parametrically, right? And we talked about parametric curves over here, right? So x of t is the I component here, and y of t is the j component over here, and the t values go between a and b, right? So this for us is going to be a parametric curve of finite length, right? Okay, so I have a parametric curve. So how we're going to work out the vector field is using this definition over here, right? Now I rewrote it here because this has a little more detail, right? So what I have is line integral of a vector field over a parametric curve C, and what you're doing is you're using the information from a parametric curve C, right? Okay, so the idea is what this x over here, right? The x you're going to replace by the x of t from your parametric curve, right? Okay, so if you want, this is the x in the parametric curve. The x in the parametric curve is a function of t, x of t. So this x over here you're going to replace by x of t, right? Similarly, the y over here you're going to replace by the y of t, right? Okay, and then what you do is from your parametric curve, you're going to differentiate. If you want this parametric curve over here, you're going to differentiate it with respect to t, right? Now, when you differentiate with respect to t, you differentiate in the components, the component functions with respect to t. So I'll get x prime t over here, and I'll get y prime t over here, and that's what I write down. So I get x prime ti plus y prime tj, and that goes inside here, right? And this is, these are vectors inside here, right? These are vectors along the curve, and these are corresponding vectors along the curve, right? These are tangent vectors. Okay, so what you're doing is you're taking the dot product of vectors over here with vectors over here, right? So that is, you have a dot product inside there. When you work out this somewhat complicated expression, this will just turn out to be a function of t, right? And this function of t, right, this is just a function of t, and when you integrate okay, so this will be a function of t, and once this is a function of t, all this is really just a definite integral of a function of t integrated, you're integrating with respect to t between limits a and b over here, right? Right, okay, so let's see an example of how this works, right? Okay, so I'm given this vector field over here, right? In a second, I will, in a minute or so, I'll do interpretation, right? But let's say focus on the calculations, right? Okay, so this is a vector field over here, 3x squared I, right? This particular vector field is a little simple because it doesn't have any j component, right? Which means that it's a horizontal vector field, right? So it's this vector field over here, this horizontal vector field. But anyway, so I have this vector field over here, right? And I want to calculate this line integral for a parametric curve which is C1, right? And the parametric curve C1, this is your parametric curve C1, right? So if you're comparing this general expression over here to this expression here, right? The x of t is equal to 1 plus t, right? The y of t is equal to 1, right? The a is equal to 0, and the b is equal to 1, right? Okay, so we're going to need that when we do any line integral, right? Right, so your line integral of your vector field, right, along your parametric curve C1, you use your definition over here, right? So using this definition here. And now you put in your information here, right? And the information here comes from the parametric curve, right? As I just said, right, the x of t is 1 plus t, right? So you're looking at the form of your parametric curve, right? You're looking at the given parametric curve. So the x of t is 1 plus t, right? So the x of t is going to be 1 plus t. Y of t is going to be 1, right? So the y of t, notice you replace by 1, right? Okay, and the x of t is 1, the x of t is 1 plus t, so that 1 plus t I need to differentiate in this formula. The formula tells me the x of t I need to be differentiating it over here. And the y of t, which is equal to 1, I also need to differentiate over here, right? So I need to differentiate, right? Okay, so one more time, right? I want to evaluate my line integral for my vector field along the curve C1, right? And how I do that is I use my definition of the line integral here, right? And in this definition of the line integral, now to actually work it out, you need to put in what the x of t and the y of t is everywhere, right? And the x of t and y of t come from your given parametric curve, right? The x of t is 1 plus t in this case. The y of t is equal to 1, right? So you put that in over here, right? And now you start to work it out, right? Okay, so this part with the differentiation is easy, right? 1 plus t here, what you're doing is you're differentiating with respect to t, right? So if I differentiate 1 plus t with respect to t, I'm going to get 1 over here, right? If I differentiate 1 with respect to t, differentiating a constant with respect to a variable t, you're going to get 0 over here, right? So here I get I plus j over here, right, for this piece. Right, so now let's focus on what this means here, right? Your vector field f of xy is 3x squared I, right? And what you have over here is not f of xy, but f of x of t, y of t, right? Okay, so what that means is wherever you see x in this expression, you're going to replace by the x of t, which is 1 plus t. Wherever you see y in this expression, you're going to replace by y of t, which is 1, right? It just so happens you don't have any y in this particular simple example. So all you need to do in this case is just replace the x over here by x of t, right? So that is actually what this statement is saying over here, right? And if I go back to this more explicit definition, right? Notice here this is f of x, and what you're doing is you're replacing the x by x of t, right? Okay, so I need to actually put in the x of t into this, right? Okay, so the x of t is 1 plus t, right? So I put in the 1 plus t over here. That's all I need to do. When I put in 1 plus t, I'm going to get 1 plus t squared, right? Right? So the 3x squared, when you put in x of t for x, which means that you put in 1 plus t for the x, you're going to get 1 plus t squared, right? So you're going to get 1 plus t squared, right? And then I. Okay, so this is the f of xt, y of t, right? This is when you substitute x of t and y of t into your vector field, right? And you want to notice that this is just, you could just really regard this is a vector over here, this is a vector over here, and now you're taking dot product, right? Now how do you take dot product? How you take dot product is you multiply the corresponding I components, you multiply the corresponding j components, and you add, right? Okay, so I multiply this 1 plus t squared, right, by 1, and I'll get 1 plus t squared. And then this doesn't have any j component, so the j component, if you want, is 0, right? And you're going to get 0 times 0 over here, which is 0, right? Okay, so yes, there's no contribution from the j component in this dot product, right? All you get in is the 1 plus t squared times the 1, which is 1 plus t squared, right? So the key thing you want to note, and I mentioned this a little earlier, is once you work out this dot product over here, you're just going to get a function of t, right? Okay, so now I just simply get a function of t. Now if you look at this just by itself, right, you want to notice this is just normal integration, right? This is integration of a single variable where the single variable is t, right? And the limits over here are 1 and 0, right? And where that 1 and 0 came from is, remember, uh, in this formula you have a and b, and a is the smaller value over here and b is the larger value over here, right? So the a is 0 and the b is 1, right? Anyway, so you have a definite integral over here of uh, this function 1 plus t squared, right? 3 times 1 plus t squared, and you integrate in between 0 and 1. This is just normal integration, right? If you're going to work this out, one way to do this is to substitute u is equal to 1 plus t. Or what you could do is you could realize this is 1 plus t squared, right? So when you integrate this, you're going to have a cubed outside this bracket. And whatever this is over here, you want to make sure that when you differentiate it, you get this. You get back here, the top over here, right? And when I differentiate this, you're going to get a 3 coming down over here. This 3, we subtract 1 to get the 2. You need to differentiate the inside and multiply, which would be 1, right? So when you differentiate this, you get this, right? But you all should know how to integrate this by now, right? As I said, next way to do this is to substitute u is equal to 1 plus t, right? Anyway, so you integrate this and you substitute t is equal to 1 and t is equal to 0. Unfortunately, this has a mistake over here, right? Because when you put 1 into this, you're going to get 1 plus 1, which is 2 cubed, which is 8, right? And then when you put the 0 in, you're going to get 1 plus 0 cubed, which is 1, right? So really, this should be 8 minus 1. So this answer is wrong, right? This should actually be 7, right? Okay, so let's take a look at the second example of calculating a line integral, alright? Okay, so it's going to be the same vector field as before, but now the parametric curve is different, right? So if you want a diagram, the first parametric curve was C1, which was the horizontal one, and the one that we're looking at now is this vertical line segment over here, right? So this is the C2 over here. Anyway, so we want to calculate it, right? And the method of calculation is very similar to what we had from before, right? Okay, so you use a definition of the line integral, which is this definition over here, right? Well, if you're using this definition, notice you have your x of t and the y of t here, right? Similarly, you have x prime and y prime, right? So what you need to do is you need to identify what the x of t is and what the y of t is, right? And the x of t and the y of t, they come from your parametric curve, right? And in this case, so the coefficient over here, the I over here is 1, right? So the x of t in this case is 1, right? So the x of t is 1, and the y of t is 1 plus t, right? And you're seeing it over here, right? In this expression, what you're doing is the x of t, you replace by 1 over here. The y of t is 1 plus t, right? And over here, what I need to do is the x of t, which is 1, I need to differentiate it with respect to t. So it's 1 over here, the x of t, and I need to differentiate it. And the y of t, I need to differentiate that with respect to t, right? Okay, so let's work out this part over here first, right? This is a little easier. You differentiate the 1 with respect to t, you're just going to get 0. And you differentiate the 1 plus t with respect to t, you're going to get 1, right? Okay, so here I get 0I plus j, which is just j, right? Now over here, right, well, what are you doing over here, right? What you're doing over here is, this means wherever you see the x, you're going to replace by x of t, right? And the x of t in this case is 1, right? And wherever you see y, you're going to replace by 1 plus t, right? But this does not have any y in it, right? So all you're doing is you're just replacing the x by x of t, which is 1, right? So you're going to get 3, 1 squared, right? Okay, so this f of xy over here, 3x squared I, is the same, alright, this f of xy, this vector field, right? What you're doing is replacing the x by x of t and the y by y of t, right? The x of t in this case is 1, the y of t is 1 plus t, right? So wherever you see the x and the y, you're going to replace by 1 and 1 plus t respectively. It just so happens that this does not have any y in it, so all you're doing is replacing the x, right? Okay, so you're going to get 3 times x of t, which is 1, so you're going to get 3, which is 1 squared. So you get 3 times 1 squared I, right? And 1 squared is just 1, and this is just going to be 3 times 1, which is just 3, right? So this is 3i over here, and then this is j over here, right? And if you take the dot product of 3i with j, right, this is just going to be 0, right? If you're not happy with this, you could write this out in column vector form, and you can check the dot product, right? But this is okay, so it's just normal dot product. You take any x component over here and you multiply it against the x component over here, which is 0, right? So you get 3 times 0, which is 0, right? And then the j component over here, you have no j component, so the j component, the coefficient of that is 0. And you multiply that by 1, so you get 1 times 0, which is 0. So this is 0 plus 0 over here, which just gives you this 0, right? And when you integrate 0, a definite integral, right, you're just going to get 0, right? If you want, you could integrate the 0, put a constant in, but when you work this out and you evaluate at 0 and 1, right, what you're going to have is c minus c, and the c minus c will give you the 0, right? Or you could just sort of take this as a fact, right, that if the integral is, the answer is just going to be 0. Right, okay, so we worked out a line integral of this vector field along two different curves, C1 and C2, right? So let's interpret the answer as work done, right? Remember I said that your a line integral can be interpreted as work done, right, by a vector field on a particle as it moves along a curve C, right? Okay, so let's look at these specific examples and see if we could interpret it in terms of work done, right? All right. Okay, so your first one, well, first of all, what's vector field, right? Your vector field that we're looking at is 3x squared I, right? Now, I think I mentioned that this doesn't have any j component, right? So if you're looking at any vector at any point, right, in the plane, right, your vectors are horizontal, right? And this is a sketch of your vector field, right? Your vectors over here are horizontal. One thing you do want to notice is that this is 3x squared I, right? So as your x increases, right? So for example, over here, this is x is equal to 1, right? And here you'd have x is equal to 2 and so on, x is equal to 3, right? Okay, so as the x increases, what's happening over here is the 3x squared would increase, right? So when you put x is equal to 1 into this, you'll get 3, right? If you put x is equal to 2 into it, you're going to get 3 times 4, which is 12, right? Put x is equal to 3 into it, you're going to get 3 times 9, which is 27, right? Okay, so this vector field, the lengths of the vectors will increase as the x increases, right? Okay, and you've seen it over here in this diagram, right? The vector fields, the length of the vectors, they actually increase as the x increases, right? As you go this way along the x-axis, the vectors increase in length, right? Okay, so this is what your vector field is going to look like. It's the main thing for us is that it's actually a horizontal vector field. Right, okay, and now what I want to do is I want to interpret my line integral along the different, well, I want to interpret the different line integrals, right? Okay, so the first one is along this curve C1, right? Now, what is this curve C1, right? Your curve C1, we looked at parametric curves and so, but one thing you want to note is if I have a parametric curve and your component over here is just a linear function, right? And the coefficient over here is also just linear, right? Okay, you have nothing involving t squared and so on, right? Or t cubed or sine t or anything like that, right? What that means for you is that this over here is just going to be a line segment, right? You do want one of these to involve t, right? If both of them were just constants, then you just have a point, right? Okay, so you have one of these over here involving t. This is a linear function. This one is constant. What that is going to imply over here is that this is a line segment, right? And if you want to graph a line segment, it's pretty easy, right? What you do is you just need the start point and you need the end point, right? You just need start and end point, right? And the start point you just get by substituting t is equal to 0 into this, right? And when you substitute t is equal to 0, you're going to get 1 over here and you're going to get a 1 over here, right? So you get the point 1, 1, which is your start point, right? To get the endpoint, what you do is you put in the t is equal to 1, right? And when you put in t is equal to 1, you get 1 plus 1, which is 2, right? And this is still 1 over here. So you get the point 2, 1, right? So the x is equal to 2, y is equal to 1. So you get the endpoint. So that's how you sketch these sort of parametric curves when you know it's a line segment. All you need is the start point and the end point. Anyway, so once I sketch these, I realize that, well, this is just a horizontal line segment, right? Okay, so my line integral is work done, right? Okay, so when I go from this point here to this point over here, right? If I have a particle moving from here to here, and this vector field is forces acting on the particle as it moves from this point to this point over here, right? You want to notice that the force is acting in the direction of motion, right? So what you have is positive work done, right, by the vector field as it goes from here to here, right? This is definitely non-zero, right? It's not negative, it's in fact positive, right? So this is, if you want, you could just, if you say you probably forgot about the fact that the lengths of the vectors over here were changing, right? The main thing is that this is really just horizontal over here, and if it's a horizontal vector field, really you in just this sort of case that we had from before here, right? You have a straight line, you have a force acting in the direction of the motion, right? And then the work done is just force times distance, right? It isn't quite so simple, right? Because in this case, the forces are in fact changing, but it's still horizontal. It's still in the direction of motion. So you'd expect that the work done going from here to here would be positive, right? And that actually agrees with the answer over here. So the answer, remember, here is supposed to be 7, right? So your work done going from here to here would be equal to 7, right, for this vector field. Right. Okay, so that's for this first one here, right? Let's look at my second line integral, right? So remember, it's the same, this example, I'm using the same vector field, right? But now I'm doing a line integral over a different curve, right? Now again, from the form of this is just a line segment. And to sketch a line segment, you simply need the start and end point, right? Okay, so if I put in t is equal to 0 into this, I'm going to get 1 over here, and I'll get a 1 over here. So this is my start point. The start point is 1, 1. And when I put t is equal to 1 into this, I'll get 1 over here and 2 over here. So the x is equal to 1, the y is equal to 2, so I get this end point over here, right? Okay, so you want to notice that this line segment is a vertical line segment. Right. Okay, so now, well, you want to consider, well, what's going to be your work done, right? Right, so your work done, this is the direction of motion, right? This is the direction of motion, but as you move along this line segment, right, all your forces are always horizontal, right? Okay, so one way to look at this is, remember, if your forces are not acting in the direction of the motion, if your force doesn't act directly, if your force doesn't act along the direction of the motion as it does, example over here, what you need to do is you need to resolve in the direction, right? Okay, so in this case, for this example, over here, the direction of motion is vertical, right? And the forces are horizontal. So if I resolve my horizontal force in the direction of the motion, right? Well, it'll be vector field, the magnitude vector field times cosine, and then the angle is now 90, right? And cosine of 90 degrees, is 0, right? So if you try to resolve your horizontal vector field in the direction of motion, you're just gonna get 0, right? So as you move along this vertical line segment, these forces are not going to do any work on the particle as it moves from here to here, right? Because well, the motion is always just perpendicular to your force vectors, right? Okay, so the work done going from here to here, that is just going to be 0, right? And that is what this worked out to be, right? Okay, so next, while we're at it over here, what we could realize here is that yeah, here what I have in this integral over here I have 3i here, right? And then this part over here, I'm taking a dot product with j, right? Okay, so what the 3i is over here, right? The 3i is in fact the forces at each point on this vertical line segment, right? So over here, the vector field would be 3i. Sorry, over here the vector would be 3i. Over here the vector would be 3i. So over here the vector would be 3i. So at each point on this line segment, the vectors are 3i, right? So that is what this 3i is, right? What this j is over here, right? That j is the direction of motion, right? And the direction of motion, you notice, is vertical, right? Okay, so your forces, the 3i, as you move along your line segment, the forces are always 3i, always horizontal, and the direction of motion is j, it's vertical, right? So when you take the dot product of your force vector with your displacement, with the direction vectors over here, right, you're going to get 0, right? And that really is similar to what we had. It's not similar, it's in fact using this expression over here, right? So what you're doing is, right, okay, so you take in dot product, okay, so it's f dot d, right? Now, so in this case, the f is the 3i over here, and the j, this isn't quite, if you inside the integral, it isn't quite displacement, it's direction of motion, right? But it's a similar idea. You take in a dot product of force with displacement, which specifies direction of motion, right? Okay, so this is your force vectors over here as you move along the curve. And this one over here is specifying direction at each point in the curve, right? And this dot product is just always going to be 0, right? So you take a dot product over here, you get 0. When you integrate 0, you just get 0. And that agrees with the fact that when you move from here to here, right, this horizontal force will do no work in the vertical direction. Okay, so we just saw a vector field in the plane, right? And for a parametric curve in the plane, such as the C1 over here, right? How to evaluate a line integral, right? And you're using your parametric description, right? So this is key when you need the information from your parametric curve to evaluate your line integral, right? And really what you're doing is you're taking the x of t over here and the y of t over here, and you're using it in your definition of your line integral, right? So the x of t, this 1 plus t will go in for this x of t over here, right? And then you put in the y of t in, which is the 1, and you put that in over here. So everywhere in this expression, you're going to, on the side, you're going to replace by the x of t and the y of t, which comes from your parametric curve that is given to you, right? Okay, so this is a line integral of a vector field, right, in the plane, right, when your parametric curve over here is in the plane also, right? Okay, so now what we want to do is we want to consider a line integral of a vector field, but now your vector field is in three-dimensional space, and similarly a parametric curve is also in a three-dimensional space, right? Okay, so we saw examples of parametric curves in three-dimensional space. Remember the helix, right? So that helix is a parametric curve in three-dimensional space, right? And we saw examples of vector fields in three-dimensional space, right? Right. I'll give you show an example of what a line integral would look like in three-dimensional space. But for the time being, let's look at the definition and see how we calculate, how we work out the problem, right? Okay, so the definition for your three-dimensional case is very similar to your definition for the two-dimensional case, right? Notice what you have over here is your parametric curve. Over here you have your parametric curve, right? Here, because it's in the plane, you just have x of t and y of t, right? But here, this is in three-dimensional space, so you have x of t, y of t, and z of t, right? The line integral, well, how do you work this out, right? What you're doing is you're going to be using your parametric curve, what's given to you, and you take the x of t and the y of t and you substitute it into your vector field, right? And you take the x of t and the y of t and you take your derivatives over here, right? Likewise over here, what you're doing is you're taking the x of t, the y of t, and the z of t, and you substitute it into the vector field, right? So that's what this is. And then you take in the derivatives, right? So you differentiate with respect to t here, here, and here, right? And then you get this expression, right? So you take your dot product of your vector field, right? Evaluate it at your parametric curve, and then you take a dot product of that with this over here, which is really tangent vectors for your parametric curve, right? But the main thing that I want you to get is that the form over here for your line integral in your three-dimensional case is really the same idea as what it was in the two-dimensional case, and the method of calculation is similar, right? Okay, so let's see the calculation, right? So what you want to do is you want to let's see an example of the calculation. So you want to take a line integral of this vector field, which is a vector field in three-dimensional space, right? With this parametric curve here, right? Okay, so you're using a definition of how you evaluate a parametric curve, how you evaluate a line integral in the case of a parametric curve. Right, what you're going to do is where in your vector field, first of all, what you're doing here is the x you're going to replace by the x of t, the y you're going to replace by the y of t, and the z you're going to replace by the z of t, right? So this x over here, you're going to replace by x of t, right? So you're going to replace by t, right? The y over here, you're going to replace by t squared, right? So when you do that, the x is going to be t, the y is going to be t squared, so you're going to get t times t squared, right? And t times t squared is t cubed, right? Which is this over here, right? Okay, so that is replacing the x and the y by the respective x of t and y of t over here, right? And likewise, this y over here and this z over here, you're going to replace by the y, which is t squared, and the z, which is t cubed, right? So you're going to get t squared times t cubed, which is t to the fifth, right? Right, and similarly for here, the z and the x, you're going to replace the z by t cubed, the x by t, right? So you'll get t cubed times t, which is t to the fourth, right? Okay, so this over here, when I replace the x by t, the y by t squared, and the z by t cubed, right? So that is what this expression means. I replace the x by t, the y by t squared, and the z by t cubed. I'm going to get this, right? And I just worked this out. This is t cubed for the I component, t to the fifth for the j component, and t to the fourth for the k component, right? Okay, so that is substituting these functions into these x of t, y of t, z of t for x, y, and z into a vector field, right? Okay, and that is actually what this says over here, right? You're supposed to replace You're supposed to have x of t for the x, y of t for the y, and z of t for the z. Anyway, so we get this piece over here, right? And the second piece where you take the derivatives is a little easier, right? This is the x of t, this is the y of t, and this is z of t, right? So the x of t is t, the y of t is t squared, the z of t is t cubed, right? And what you're doing is you're going to differentiate each of these with respect to t, right? When you differentiate the t with respect to t, you're going to get 1. Differentiate the t squared with respect to t, you're going to get 2t. Differentiate the t cubed with respect to t, you're going to get 3t squared, right? Right, so what you end up getting over here is 1, you're going to get I plus 2tj plus 3t squared k, right? Okay, so notice over here you have a vector with expressions of t in it for the components. Likewise, you have the same sort of vector, and now what you're doing is you're taking dot product here, right? And taking dot product is going to be t cubed times 1, which gives me this t cubed. T to the 5th times this 2t, which gives me 2t to the 6th, right? And then t to the 4th times this 3t squared, right, gives me 3t to the 6th, right? And remember, when you take a dot product of each of these, you need to add them up, right? So add this up over here, right? And then you integrate this. This is just normal integration. This is t cubed over here. This is 5t to the 6th, right? You're just using power rule. This will give you t to the 4th on 4. This is 5t to the 7th, 5t to the 6th, right? And when you integrate this, you're going to get 5t to the 7 on 7, right? So you get this expression. And you substitute your 1 and 0, and you're going to get this answer, which is 27 on 8, right? Right, okay, so let's look at this example. This is an illustration of a line integral in three-dimensional space, right? Probably it's not the best picture, right? So this is your x-axis over here, right? This is your y-axis over here, and this is your z-axis over here, right? Okay, so the actual parametric curve is this green curve here, right? Okay, and you see in that this particle here is moving along your parametric curve, right? Okay, right, so a particle is moving along your parametric curve, and at each point on your parametric curve, what you have is you're going to have vectors, right? You're going to have a vector from the vector field, right? Okay, and what's going to happen is as it passes through that point, right, the force vector will act on it and impart energy on the particle, right? So your vector field will be doing work on the particle as it moves through your three-dimensional space. This is not the example. This is not an illustration of this example over here, right? One way to see that is this here. The start point and the end point for your parametric curve are different, right? This one over here, this is closed, right? If you notice, this is moving in a loop, right? Okay, so it's not the same as the vector field, and your parametric curve over here is not the same as this, right? This was a graphic that I found, right? A separate graphic. Okay, so final thing over here is let's just say that we start over here, right? And what's going to happen is that the particle is moving along the curve, right? And the work is being done by the vector field until it reaches back to this point right there, right? And once it makes one loop like that, right, the work done as it travels along one loop like that, that is actually equal to the line integral along your parametric curve in this case.